Okay, so this problem says okay, so this problem says, suppose the parallel plate capacitor shown below is accumulating charge at a rate of 0.01 coulombs per second. What's the induced magnetic field at a distance of 10 centimeters from the capacitor? Okay, so we are going to use one of Maxwell's equations to solve this. And curl of B is equal to mu naught J plus epsilon naught mu naught del E by del T. Okay, so this is what we're going to use. J is, so again, what I'm going to do is I'm going to draw another side view, side view of this thing. Here's the current flowing in. These are parallel plate capacitors. Okay. So the current is, what's happening is you can think of it as positive charges flowing here, and so this is charging this plate positive, which is creating an electric field in this direction. And we are going to calculate the magnetic field due to this changing electric field. So this is the electric field, and we're going to calculate the magnetic field 10 centimeters from the center. Okay, so somewhere here, and the magnetic field here will be pointing into the sheet of the paper, and here's how you, okay, so I'll tell that to you and show that to you in a second. So let me draw this circle, and the magnetic field is tangent like that. Okay. Now we are calculating the magnetic field due to this guy. There's no physical current there, so that is 0. Okay. So what you're doing is, so this one could show up in the recording. Here's what's happening. So here are the parallel plates. The electric field is increasing in this direction. There's no physical current there. The physical current is over there. And we are going to, so this field is going, this current, changing electric field is going to produce a magnetic field like that. Your thumb is pointing in the direction of the electric field, and the magnetic field will be like that. Okay? So we will, yes?
In that first half, it cancels because the current density in that area is 0?
No, there's no physical current flowing. The physical current is flowing in the wire. So if you did that integral over here, then physical current would not be 0, and the electric field would be 0. Okay. By the way, so this is an ideal capacitor, and the electric field is only within the capacitor plates. Okay. So what we're going to do is we're going to use Stokes' theorem. But what we'll do is we'll take an integral, and the area is so this is the area over which we're taking the integral, dA. I'll draw that over there, and that's equal to epsilon naught mu naught del E by del T dA. So we'll take that integral. All right, I'll need a page, so let me add a page below. All right, so this, the left-hand side, okay, I'll rewrite that equation here. Curl of B dA equal to epsilon naught mu naught del by del T E dot dA. Okay, we'll come to that in a second. This from Stokes' theorem is equal to a line integral, and that's equal to epsilon naught mu naught del by del t E dot du. Okay, now we'll have to express this in terms of the charge and so on. Now going back to the capacitor, so here's the capacitor. The electric field is related to the potential difference like so, E times D. Okay. The electric field times the distance between the plates is equal to the voltage across the plates. And V is, okay, so for a capacitor, C is Q over V. So V is Q over C. Okay. So Q over C is E times D. And so E, the electric field is QC divided by D. Okay. And also the capacitance is equal to, what do they give us? Okay, so the capacitance is epsilon naught A by D. Okay. So we're going to substitute that. Q epsilon naught A over D times D. Okay, so that cancels, and that's the area of the plate. All right. Let me add another page below here. Okay, so what we have expressed is the electric field in terms of the charge on the capacitor plates. Q divided by epsilon naught A. Okay. Now what we are interested in is del E by del T. How is the electric field changing with time? And that's equal to epsilon naught A times del Q by del T. The rate at which the capacitor is being charged. And that's equal to the current flowing into the capacitor. Okay. All right. Now, so we'll substitute that. Del E by del T is that. Epsilon naught divided by area. Now, this integral on the right is just, so the electric field is, and that's the electric flux. This is the electric flux. And so that's the electric field times the area of the plate. So this is equal to, so let me write this as epsilon naught mu naught del by del T of E times the area of the plate. Okay. And so now we're going to take all of this and, all right, so write it over here. So now what we have is, okay, this has become a little messy. B dot ds, this is the line integral. That's the left-hand side, is equal to epsilon naught mu naught del E by del T. Del E by del T is 1 over epsilon naught AI times A, the area, and the area of the plate cancels. All right, now let me show you the line integral. So the line integral is over this big circle whose radius is r, which is 10 centimeters in the problem. We'll call it r. So the value of the line integral is just b times 2 pi r. Okay. So b times 2 pi r is equal to epsilon naught. The epsilon naught cancels. Okay, so actually let me, the epsilon naught cancels, so it's mu naught I over n I. That's it. Okay, so the magnetic field is mu naught I over 2 pi r. Okay, so if you go back and look at your notes, that's the exact expression for a magnetic field from an infinitely long conductor carrying a current I at a distance r. Okay. So what we are saying is this current that was feeding into the capacitor plate. Now, between the capacitor plates, it's only the electric field that's changing. And that changing electric field is producing the exact same field. Okay. So now we can evaluate this. Okay, so let me add another page and I will do that. So now the strength of the magnetic field is mu naught I times 2 pi r. Mu naught is 4 pi times 10 minus 7 Tesla meter per amp. And the current flowing in is 0.01 coulombs per second, amperes. 2 pi, and we're finding the magnetic field at a distance r, 10 centimeters, which is 0.1 meters. All right, so let's take care of powers of 10 first. That's 10 minus 7, 10 minus 9, 10 minus 8, 2. Okay, so 2 times 10 minus 8 Tesla. Okay, so that's the magnetic field at that distance. Or we'll write it as 20 nanotesla. And that's roughly 1,000 times the Earth's magnetic field. Okay. Any questions before I? Okay.